if we want to launch a spacecraft from the surface of the Earth, in this case, we are looking at a point here. Depending on the speed that we apply in the beginning, the velocity of the spacecraft, it has different paths. If it's really low, it'll just go here and as a projectile is come to point A. And if we increase the speed a little bit more, it'll come here. And little bit more, what will happen is it's still a projectile, but the path is parallel to the curvature of the Earth. So it will follow a circular orbit and it'll continue its orbit. So depending on the velocity that we apply at the launch, it follows different paths. So this is a circular one. And if we increase the speed a little bit more, it'll go through an elliptical path. That's what the planets normally go in, elliptical paths. But if we increase the speed a bit more, what will happen is the spacecraft will escape the gravitational field of Earth. So it will go away and it will never come back. So what we have found out here is that the VA is basically the velocity we apply to get the spacecraft to point A is less than VB, which is less than VC. VC is basically the initial velocity that we applied to get the spacecraft in the orbit, and then that's less than VD, and which is less than VE. So VE is the escape velocity. So escape velocity is basically the minimum velocity that's required to get the spacecraft to a place that is escape the gravitational force of Earth. So it goes to infinity. So it will not come back, because we looked at here that at A it's coming here, at B it's coming here, and C is going on a circular orbit, and D is going in an elliptical orbit. But VE is the velocity at which that particular object, in our case it's a spacecraft, escapes our gravitational field. So how do we find the escape velocity, the minimum velocity that we need to get the object outside the gravitational force of Earth? What we are going to use is we are going to use the law of conservation of energy. So in our case, there are two energy that we are looking at. One is the kinetic energy and one is the potential energy. So when we have the object here, the object has got some kinetic energy and it has got the potential energy. And here it has escaped the gravitational force of Earth. So we are going to consider this as infinity. So there's a potential energy and kinetic energy here as well. So let's consider the potential energy as UF here, and here F is the kinetic energy, and here the potential energy is UI, and the kinetic energy is Ki. So what happens is that at this point, the point here, the object has lots of kinetic energy but less potential energy. But at this point on the path, what is happening is that the kinetic energy is transferred into potential energy. So kinetic energy is being reduced and the UI will keep increasing. Regarding the velocity, let's assume the velocity here is VI, here VF. So from the previous videos that we found out that the potential energy at a distance r from the center of Earth is given by UR is equal to minus GMM over R. So now we write the equations for UI and KI, UF and KF. So UI is equal to minus GMM over r. So r in this case, the distance from here to here, r. Ki is equal to half mvi squared. Now uf is equal to, that's our potential energy at infinity, is going to be minus gm m over infinity, because that's where we are going to take the object to free the object from the gravitational potential of Earth. And kf is equal to half mvf squared. So now when we look at all these four equations, so one is ui and ki, uf and kf. When we provide a force here, so we are giving some energy to this spacecraft. So this has both potential and kinetic energy. As it follows the path, what happens is that the kinetic energy is transferred into potential energy. So at the middle here, what is happening is that ui will be increasing and ki is decreasing. So it comes to a place, all the kinetic energy is transformed into potential energy. So we are expecting the velocity of the object to be zero. I mean, we can give more energy so that it'll have some kinetic energy when it comes here, but we want to find the minimum velocity that we need to bring the object here. So this is infinity. That means this value is going to be zero, because if you divide a number by infinity, that is zero. And here we are expecting the final velocity to be zero, because we want to find the minimum escape velocity that we need to bring the object to infinity. So we expect the velocity at infinity to be zero. So this value is going to be zero as well. So if we now use the law of conservation of energy, so ui plus ki is equal to uf plus kf. So the energy in the beginning is same as the energy at the end. So ui is this and ki is this. So if we write all these equations again, so ui plus ki is equal to uf plus kf. So what is ui? Minus gm m over r plus ki is equal to half mvi squared is equal to uf is equal to minus em m over infinity plus half mvf squared. And because vf is zero, and uf is also zero. Why? Because we are dividing by infinity here. So that means minus gmm over r plus half mvi squared is equal to 0. So from here, that vi is our escape velocity we are trying to find. So half mvi squared is equal to gmm over r. So from here we find out vi, which is actually the ve, is equal to, will cancel each other. So we multiply by 2, and so v is equal to 2 gm over r. And we need to have a square root here. So that's the escape velocity. But we found in another previous video that an orbital velocity is given by my gm over r. So that means there is a relationship between escape velocity and the orbital velocity. What we are doing is we are multiplying by root 2. So we can say that VE is actually root 2 of orbital velocity. So what we have found is that the escape velocity is square root of 2gm over r and orbital velocity is gm over r. So what we see from here, the escape velocity or the orbital velocity, they don't depend on the mass of the object or the mass of the spacecraft, but it depends on the mass of the planet. And also, it's inversely proportional to the radius. So if the spacecraft is far away from the planet, the escape velocity is not that much. But if it's close to the planet, we need to provide more force, more velocity for the object to escape the planet. So if I have a planet here, and so the object is here, there's another orbit here, and mass of the planet is capital M, and these two objects, this is M1 and this is M2, and the radius of this one is R1 and this is R2. So we have these two satellites or spacecraft orbiting the planet at radius R1 and R2. So we want to find out the escape velocity for M1 and M2. So the escape velocity for M1 is, M1 is equal to 2gm over R1. And escape velocity for M2 is equal to 2gm over R2. So what we know from here is that R2 is greater than R1. So that means Vm2 must be V less than Vm1. So if the object is at a further distance from the other orbit, that means the escape velocity is less than the escape velocity of an object in an orbit which is below the other orbit. So in summary, what we have found out is that if we are launching a rocket from Earth, or there is a satellite already orbiting the Earth, and we found out the escape velocity, the velocity that's required to move these objects to infinity. So for these two instances, the escape velocity is equal to square root of gm over r. This is g. So this question is about calculate the escape velocity for the International Space Station in orbit 400 kilometers above the surface of Earth. International Space Station is a lower Earth orbit satellite. That means it's not far from the Earth's surface, about 400 kilometers. So if we want to find the escape velocity of this International Space Station, so this is Earth, and this is the center of Earth. So say for instance we have the International Space Station orbiting the Earth here. So the distance from here, this is 6370 kilometer, and then we have got 400 kilometer here. So the mass of Earth is given and the radius of Earth is given. So what we want to find out, we use the formula that we derived before for the escape velocity. So the V escape is equal to square root of 2 gm over r. So all that we need to do is we just need to put those values here and find the answer. So V escape is equal to, so square root of 2 times g is 6.67 times 10 to the power minus 11, And then for the mass, we have to put that in. It is 5.97 times 10 to the power 24 divided by, we have got radius in, that should be in meters, so it's going to be 6370 plus 400 times 10 to the power 3, because 6370 is kilometer and 400 kilometer, and 10 to the power 3 because to convert that into meter. So the answer will be 1.0846, that is times 10 to the power 4. We will get meter per second, or we can also write it as 10.8 kilometer per second. So that's the escape velocity. So that's the velocity we have to provide to the International Space Station here, for the International Space Station to escape the gravitational force of Earth, so that it will go and it will never come back.